Hello friends, welcome back to this video. In this video, we'll be talking about the figure of merit of double sideband full carrier type of amplitude modulation receiver using the envelope detector. So we are talking about DSB FC receiver and which is envelope detector. We all know that in the case of DSB FC, we can have envelope detector as well as synchronous detector. I hope you remember what was synchronous or coherent detector. Synchronous and coherent are both the name of the same receiver. So here we are just focusing on the envelope detector and we'll be talking about the figure of merit. So I have already talked about the figure of merit. What was the figure of merit? Figure of merit was equal to the output SNR upon the input SNR. But now here if I am talking about a specific type of amplitude modulation, here we will be using the figure of merit equal to the output SNR upon channel SNR. So now why I am using the channel SNR here? Because in the channel only we have different modulated signal. So if I want to compare different signals at the input, all of them will be same. In the channel only there arise a difference. So I'll be talking about the figure of merit which is equal to, so I am denoting the figure of merit by FOM. It is equal to output SNR upon channel SNR. So now here the task is to find out the output SNR and the channel SNR. Will divide both of them and we'll get the figure of merit. But this is something which is the trickiest portion of this video. So here we'll be talking about the modulated signal. So the modulated signal is added to the noise. So I am denoting noise by WT. So in the channel it is added to the noise. So here we have a band pass filter at the input of the receiver. I hope you remember why we are using the band pass filter at the input of the receiver. We are using the band pass filter at the input of the receiver so that I can extract only those components of the modulated signal where signal is present. At rest of the places only noise is present and I am not concerned about that noise. So now here if I talk about the band pass filter, so here it is used to remove the excess noise. So after that we have, as the name suggests, we have the envelope detector. So here we will be getting the output Y of t and here we will be observing what is the SNR here at the output and what is the SNR here at the channel. So now first I will be talking about the channel SNR. So now I know what is empty. Empty you all know. What was the formula to find out empty in the case of double sideband full carrier type of amplitude modulation? It was equal to AC 1 plus m of xt into cos omega c t, or you can write it as cos 2 pi fct, both are same. So now I have mt is equal to AC 1 plus m of xt cos omega c t. So now if I need to find out SNR of the channel, so SNR of the channel will be equal to, so it will be power of the signal in the channel and I am denoting it with PSC, and power of the noise in the channel. So power of the noise in the channel. So first I need to find out the power of the signal in the channel. So now here to find out the power of the signal in the channel we'll be using E of m square t. So we'll be taking this modulated signal, will square it, will take the mean, it will give me the power. I have talked about it several times. So what is m square t? So here we'll put the m square t. It will be AC square 1 plus m of xt square cos square 2 pi fct. So now here this is, I need to find out the power of the signal in the channel. So I'll just simplify it. Here I'll be having AC square. So I'll expand this square and I'll be having 1 plus m square x square t plus 2m of xt into cos square 2 pi fct. Now I'll further simplify this. Here I'll be having ac square cos square 2 pi fct plus ac square m square x square t cos square 2 pi fct plus 2m xt cos square 2 pi fct. So now here one thing you should know is that cos square 2 pi fct can be represented as 1 plus cos 2 theta. So this is cos square theta can be represented as 1 plus cos 2 theta upon 2. So what will be the cos 2 theta? It will be cos 4 pi fct upon 2. So now here I'll replace all these cos square 2 pi fct by 1 plus cos 4 pi fct. So here I'll be having e of ac square 1 plus cos 4 pi fct upon 2. So here I'll be taking the e, because e is a linear function. I am already saying this from like past 2-3 videos that e is a linear function. So here we'll be having ac square m square x square t. So again cos square 2 pi fct can be written as 1 plus cos 4 pi fct upon 2. So now here this is e of 2m xt cos square 2 pi fct. So here I have not changed cos square. I'll be telling you why. So here we have e of ac square upon 2, which will be ac square upon 2. So here I am directly putting it as ac square upon 2. Now here we have mean of cos 4 pi fct. So here one thing you should know, that mean of cos 4 pi fct will be equal to 0, because cos is a full wave. So if I take the cos, so here if I take the mean, because it has positive and negative parts which are equal, so both of them will cancel out in the full wave. So here the mean will be 0, because equal negative and positive part will cancel out each other. So here this mean is 0. So here I am using this property, I am neglecting this because this mean will be 0. Similarly this mean will be 0. So here we'll be having ac square m square x square t mean upon 2. So now here we have mean of xt. So I can write it as 2m mean of xt into mean of cos square 2 pi fct. So now whenever I used to denote my xt was the input signal, xt was again symmetric around the origin. So now here if this is my xt, so this is minus w, this is w, and now this is my f of x of f. So now here this is my x of f. So now here you can see directly the mean will be 0 for this function. It's a uniform distribution. Here the mean will be 0. So always the xt will be symmetric around the origin. So here the mean will be 0. So now here this is 0. So this whole term will be 0. So if I talk about the power of the signal in the channel, so it is ac square upon 2 plus ac square m square e of x square t upon 2. So what is e of x square t? Again it represents the power of the input signal. So here it is equal to AC square upon 2 plus AC square m square. This is the power of x. So it is P of x upon 2. So now here I can take AC square upon 2 common. Here I'll be having 1 plus m square px common. So now this is my power of the signal in the channel. So the next thing I need to find out the power of the noise in the channel. So now if I talk about the noise, so the noise is also confirmed to this bandwidth omega to minus omega, and it has the amplitude n0 by 2. So this was the power spectral density of the noise. So this is the frequency axis, this is S of f. So if I talk about the power spectral density of noise in the channel, so noise in the channel will look like this. I have already talked about the noise and the band limited noise, because here we don't have the additive white Gaussian noise from minus infinity to infinity. So here we have band limited noise. So this noise is found out using this band pass filter in the channel. So now here, so this noise is having the definite power. So it is not having infinite power, it has the definite power. So we'll be finding out the power of the noise in the channel. So what will be the power? This is the power spectral density. So from the power spectral density, if I need to find out the power, what will I do? The power spectral density, when multiplied with the area, it will give me the power. So the power spectral density's area will give me the power. So the all over area of this portion will give me the noise power in the channel. So here what will be the area? So this width is 2W and this height is n0 by 2. So the power of the noise is n0 W. Now coming to the signal to noise ratio of the channel. So now I can easily find out SNR of the channel. What will be the SNR of the channel? SNR of the channel will be power of the signal in the channel divided by power of the noise in the channel. We now know both of them. So power of the signal in the channel is AC square upon 2 1 plus m square px upon n0 W. So now I hope you understood up to this point how I can find out the SNR of the channel. Now the task is to find out the SNR of the output. So now here if I talk about the noise at the output, so NT can be represented as NIT cos 2 pi FCT plus NQT sin 2 pi FCT. So this is how I represent the in-phase and quadrature component of the noise. So this is the noise. Now this noise will get added to the modulated signal at the output. So here the output I'll be taking ST. So ST will be MT plus NT. So now it will be equal to, what was my MT? MT was AC 1 plus m of xt cos 2 pi FCT plus NIT cos 2 pi FCT plus NQT sin 2 pi FCT. So this is T. So now here this is my ST. ST is the modulated signal plus noise, because here at the receiver we'll be having the signal plus noise and we'll be processing the signal plus noise here. So here we have the envelope detector. So the envelope detector is detecting the envelope, so we'll be seeing the envelope of this signal. So this signal, which is ST, which is modulated signal plus noise, we need to find out its envelope. So this envelope will give me the output. So we'll be seeing what is the envelope of this signal. So here if I simplify this equation, I can write it as AC 1 plus m of xt plus NIT cos 2 pi fct plus NQT sin 2 pi fct. So what I have done, it is multiplied by cos, it is also multiplied by cos. So I have taken this cos common. So here I have AC 1 plus m of xt plus NIT into cos 2 pi fct plus NQT sin 2 pi fct. So now this is in the form of A cos theta plus B sin theta. So now if I need to find out the envelope will be equal to under root A square plus B square. So here we'll be having the envelope. So y dash t will be equal to under root AC square 1 plus m of xt square plus ni square t. Sorry, this is full x, so here we'll be taking square plus nq square t. So now this is AC 1 plus m of xt plus NIT whole square. This is my A square. So this is my B, nq square. So under root A square plus B square gives me the envelope. So here if I see this, AC will be a very high value, Ni will be a comparatively lower value, but NQ, if I compare NQ with this term, it is very less. So I can neglect NQ. So NQT can be neglected. So now here y dash t can be represented as, so it is not equal to, it is approximately equal to AC 1 plus m of xt plus NIT. So now here I can simplify this and write it as AC plus AC m of xt plus NIT. So now what are these things? So this is my DC term, this is my signal, and this is my noise. So now here we can reconstruct our signal. So now here the signal power at the output can be represented using this equation. So here we'll be having E of AC square m square x square t gives me the signal power at the output. So it will be equal to AC square m square E of x square t, which is equal to E of x square t is the power of x, so I am representing it with px again. So now here I already found out the power of the signal at the output. Now I need to know the power of the noise at the output. So here I'll be using the power spectral density of in-phase component and the quadrature component. So SNI comma SNQ I need to find out. I already told you SNI and SNQ were equal to SF minus FC plus SF plus FC. So here we have a component of the noise at FC and a component of the noise at minus FC. So both have the amplitude N0 by W, sorry N0 by 2, and the width is 2W. So this is 2W here, this is 2W here as well. So now I have already talked about the in-phase and quadrature component when I was discussing about the noise. So I hope you know about this. The in-phase and quadrature component of the noise can be represented using the noise power spectral density F at F minus FC and at F plus FC. So the same power spectral density is shifted at FC and minus FC. So now here we have two components. So now again I need to find out the power. So power of the noise at the output will be equal to this power plus this power. So this power was equal to, I have already found out it was equal to N0 W. So N0 W plus N0 W. So here I will be having 2 N0 W because we have two same components which were one here. So now here if I need to find out SNR of the output, it will be equal to power of the signal at the output, which is AC square m square px, upon the power of the noise at output, which is 2 n naught w. So now we can easily find out the figure of merit. So figure of merit will be equal to SNR of output, which is AC square m square px upon 2 n naught w. It is divided by AC square by 2 1 plus m square px upon n naught w. So it will be in the numerator. So now I'll just cancel out the things. So here n naught w will get cancelled out, this 2 and this 2, AC square and AC square. So here I have m square p of x upon 1 plus m square p of x. So now when I have the sinusoidal signal, so that time the power of x can be represented as, I hope you know the power of the sinusoidal signal. So it is ax square upon 2 upon 1 plus m square ax square upon 2. So now here we can use the formula that m into ax is equal to mu. So now figure of merit can be easily found out as mu square upon 2 plus mu square. So now this was equal to the efficiency. I have already found out the efficiency. So now here I found out that the figure of merit is equal to the efficiency in the case of double sideband full carrier type of amplitude modulation using envelope detector receiver. So here if I found out the output signal to noise ratio divided by the channel signal to noise ratio, which gives me the figure of merit, it is equal to the efficiency. I have already talked about the efficiency, it was having the same formula. So now I'll be concluding my session here. If you still have any doubt in any of the section, you can put your doubt in the comment and I'll try to resolve it as soon as possible. I hope you like this video. If you like it, share it with your friends, subscribe the channel and push the like button. Thank you.